Okay, we're going to kind of go through this one section at a time. I've got lots of notes, and I also have for you some sample problems here that I'm going to work through. If you do this the right way, you will have already tried these sample problems. You're going to need some graph paper for some of these because I didn't even have space for graphs. But you're try those first and then kind of follow through the rest of this video so you can see if you're doing these correctly. Okay, section 1 is on parabolas or quadratic functions. Quadratic functions typically are defined by f of x equals ax squared plus bx plus c, where a, b, and c are all real numbers, and of course you can't have 0 here because that would knock out the x squared. So the graph of this, of course, is a parabola, which is a U-shaped looking thing. It either opens upward or downward, and right down the middle of it is what we call the axis of symmetry. And where the axis of symmetry crosses the actual curved parabola, that points the vertex. So you can see here for a quadratic function, this one a greater than 0, I went ahead and just for convenience sake I put it over here in what would be the second quadrant, and I drew in a sample what would be the axis of symmetry, and of course where the axis of symmetry intersects the parabola, that's your vertex. Same thing over here, only the difference being that a is less than 0, so it opens downward. And I try to draw these symmetrically, but I freehanded them, so you could probably do a little bit better than that. But you need to know the basic information here. Of course, you need to be able to find the vertex. You need to be able to find the axis of symmetry, and you also need to be able to find intercepts. Now, if the equation is transformed by completing the square from this form to this form, this is what the book calls standard form and what a lot of textbooks call vertex form. The vertex, of course, vertex form here, I'm going to put a parenthesis there. The vertex, if it's written in this form, is hk. So you can look right at it, but notice it's x minus the h and it's a plus k on the outside. So it's kind of the opposite of what it looks like inside and exactly what it looks like on the outside. You take this guy here, you complete the square, and you can make it look like this guy. Now, if it isn't easy to complete the square, and that's one of the skills you need to be able to do, then what you can do to find the vertex, since you don't have the hk all laid out for you in this form, is to use this little formula right here, and that will give you the x value of the vertex. So that's the x value, and once you have the x value, then you plug it in, and you find the y value that goes with it. But what's kind of nice about the x value here is that the axis of symmetry is a vertical line. So the axis of symmetry will always be in the form x equals a number. Well, it's going to be x equals this number. This is the actual equation of the axis of symmetry. X equals the opposite of b over 2a. So not only does the opposite of b over 2a give you the x value of the vertex, it also gives you what you need for the axis of symmetry. Now, you change this into this by completing the square. So we're going to practice completing the square, but before we do, I'm just going to make a sketch here of a quadratic function that is in vertex form or standard form. So I have some graph paper close by. I'm going to move this up a little bit. Now, if all I have is this, and they ask for a sketch, and they're probably going to ask for you to do some graphing of parabolas and such, my suggestion is go ahead and make a t-chart. First, find the vertex, and in this case, the vertex is 1, negative 2. That's the h, that's the k. The opposite of what it looks like inside, exactly what it looks like on the outside. Make a t-chart. Be careful plugging values in. You will need 5 points, and you already have 1. You have the vertex. So I'll put the vertex in the middle as 1, negative 2. And since I don't have any weird fractions or anything like that, I usually like to go 1 bigger, 1 smaller. So 1 bigger, look at the x values here for my t-chart. 1 bigger is a 2, 1 smaller is a 0, 2 bigger is a 3, 2 smaller is a negative 1. If you do it this way, then you can use the symmetry of the graph, and these y values will be the same, and these y values will be the same. So you won't have to plug in 4 numbers, you're only going to have to plug in 2. So I'm going to make my sketch here in just a second, but first things first, I'm going to plug these numbers in. So I'll plug 3 in. 3 minus 1 is 2. 2 squared is 4. 4 times 2 is 8. Minus 2 is 6. So this is a 6. This will be a 6. Then I'll plug 2 in. 2 minus 1 is 1. 1 squared is 1. Times 2 is 2. Minus 2 is 0. Well, this is kind of neat. I not only we're able to find 5 points, I actually have the x-intercepts right here, because you can see that the y values are 0. This is not only an x-intercept, this is also a y-intercept, because this is the origin, it's on the y-axis. So now what I'm going to do, and I don't have to make a big graph for this one because the numbers aren't all that big, but I'll make it big enough that I can get a 6 in there, is I'm going to use a straight edge. Well, I'm not, you should. Set your scale, so that they're each worth 1, and then plot these points. So I have negative 1, 1, 2, 3, 4, 5, 6. 6 is up here. I have 0, 0. I have my vertex, which is 1, negative 2. I have 2, 0. And I have 3, 6. Now, when you get done plotting these 5 points, look at the 5 points and see if they don't look like they form a U-shape. And you just have to draw a smooth curve. Now, you're wondering, maybe you're wondering, why is it a little bit skinnier than most of the regular parabolas I've been graphing? It's because of this 2. This 2 stretches it vertically and makes it a little bit skinnier. Well, I'm not doing a very good job here. I think I'd be better at it after all these years. There we go. And there's the sketch of my parabola. Okay? Not so bad. Next, I want to rewrite the function in vertex form. So that's going to involve completing the square. And then I want to find the vertex and the axis of symmetry. And I'm also going to find the intercepts this time. I found them last time kind of conveniently. I'm going to find the intercepts and then I'm going to sketch it. So don't lose that graph paper. I'm going to need that back in just a second. To complete the square here, your coefficient of your x squared term must be a positive 1, and it is not. It's a negative 1. That negative is like a negative 1 there. So I am going to factor out of the 2 terms that have the variable, I'm going to factor out a negative 1. So that would leave x squared, and then a negative 1 out of a negative 2 would leave a plus 2x. Leave a little bit of a space, and then put your plus 3 on the outside there like that. Remember, the flare, to complete the square, you take half of this, which would be positive 1, and you square it. So you add 1 there. Now normally, if we add something to one side, we add it to the other, but that's not what we're going to do here. We're going to balance it, because we want the f of x by itself. We're going to balance it out on the same side. So whatever we do to the right side, we have to do the opposite of it also. And it looks like, since we added 1, I need to subtract 1. But in this case, because of this number out in front, I didn't really add a 1. This negative 1, if I was to simplify, I would distribute. This negative 1 would be times this positive 1. That would be a negative 1. So I've actually subtracted 1. I've got to add 1. Subtracting 1 and adding 1 on the same side balance out. Now I know it doesn't look like I subtracted 1, but I did because of this negative 1 here that would be multiplied times it. Be aware of that. We'll do another one of those here in just a minute. Can you see this okay? You should be able to see this okay. So this is negative 1. This is a perfect square trinomial, so I can write it as a binomial squared. And this is going to be an x, and this is going to be a 1 and a plus sign right there. It's whatever's being squared here, whatever's being squared here, and the same sign right there. So that tells me that my vertex is negative 1, positive 4. Also, look at A here. It's negative. I know that my graph is going to open downward. So I've got all sorts of stuff here that I got to keep track of. Now I also want the axis of symmetry, which you may or may not be able to see there. And the axis of symmetry is the vertical, I'm going to just abbreviate it, axis of symmetry here, is the vertical line, so it's always x equals a number. And it goes through the vertex, so it has to have the same x value as the vertex, so it's x equals negative 1. And that's the equation of the axis. Don't just put a negative 1 down, write it as an equation there. Now I need the intercepts. To get the intercepts, I'm going to set, here, first let me write it over here again, so you can see it. I went ahead and wrote it as a y instead of an f of x. To find the x-intercept, you make y equal to 0. Now looks like, because it's quadratic, I have to factor, but I'm not crazy about a negative out in front. So I'll multiply through both sides. In fact, I'm going to flip both sides and multiply through by negative 1. I get x squared plus 2x minus 3 equals 0. I get x plus 3 times x minus 1. This one actually factors, which is nice. So I get x equals negative 3 and x equals positive 1. So my x-intercepts are -3, 0, and 1, 0. Remember, write your intercepts, it's a -3, not a very good one there, as ordered pairs. Though just write down these numbers, okay? Write them as ordered pairs. My y-intercept is what happens when I set x equal to 0 and solve for y. So if I set x equal to 0, I put a 0 in for the x in both spots. This one kind of falls apart here. I just get y equals 3. So my y-intercept is 0, 3. Hopefully you can see that okay. Now between the vertex, these two x-intercepts, and that y-intercept, that might be enough to come up with a decent sketch. So when we come over here, draw another set of axes here. I've been thinking I would have had this done in advance. It looks like it opens downward and a 4. So I think I can get away with putting a line right here. Set your scale. So now I'm going to graph some points. I have the vertex is at -1, 4. Can you see this? I think you can see this still. That's right there. I have -3, 0. I have 1, 0. And I have 0, 3. Well, I don't think I'm going to need a t-chart on this one because I already see my symmetry right here, especially since I have the x-intercepts. And look, if I go down 1 and right 1 and have a point, I go down 1 and left 1, I'd have another point. See that symmetry? And so now to make the sketch, now finding x-intercepts is pretty much the same thing as finding zeros to a function, which we're going to spend some time on as well. Because to find the zeros for the function, you're finding the x values that make the y 0. Okay? That make your function equal to 0. We just write zeros as numbers. We don't write them as ordered pairs. All right, now, let's try a couple to complete the square here. This one, f of x equals 2x squared plus 8x minus 1. See, I have a number in front of the x squared that's not a 1. So I'm going to have to factor that out like I did in the problem before that. I'm going to factor it out of the two terms that have the variable. That would give me x squared plus 4x. I'll leave a little bit of space and a minus 1. Now it's convenient when this is just x squared, but if it isn't, you got to do the step. If it is, then it makes it even easier. You can just start hacking right into it. Take half of the 4 and square it, and that's a 4. But again, I didn't add 4 because of this number out in front. I added 8, so I have to subtract 8 to keep it balanced. So I have f of x is equal to 2 times, I have a binomial squared and a minus 9 on the end. What goes in here? Well, what's squared here is an x, and what's squared here is a 2, and a plus sign right there tells me a plus sign right there. Now this one here, I don't know if you're going to have any of this messy. This one has a fraction coming up. I'm going to factor out, as you can see, my lead coefficient is not a 1. I'm going to have to factor out a 3 out of the first two terms here. As that gives me x squared minus 3x, and I'll leave a space, and I'll put the plus 1 on the end. And so what I'd have to do here to find this number is you take this number, the coefficient of the x, it's -3, you take half of -3. Well, half of -3 is -3 over 2. Don't go decimal, leave it as a fraction. And then I've got to square it. So that's -3 over 2 times -3 over 2 is positive 9 over 4. So I have to add 9 over 4 here. But I didn't really add 9 over 4 here, did I? Because of this 3 that's times it, I added 27 over 4. Because 3 over 1 times 9 over 4 is 27 over 4. So I'd have to subtract 27 over 4 from both sides. Like I said, I don't know if he's going to have anything this messy. And then you'd have to, think of 1 as 4 over 4. 4 over 4 minus 27 over 4 is negative 23 over 4, or minus 23 fourths. This would be an x. What's being squared here? Well, 3 over 2. And what goes in the middle? A minus sign. And that's how you would complete the square. What a mess. So I would have f of x equal to that. Now, he's listed this as one of the skills for your test, so you're going to need to know how to do this. If you're unsure, you just got to practice it a little bit. There's lots of good examples in the book. Now, along with quadratic functions, since you have the vertex, which is a kind of a point that's either at the bottom of your graph or at the top of your graph, then we can talk about the idea of minimum values to the function and maximum values. Now the values are the y's. Do you see how the y's go vertically here? So this is the smallest y value of any point on this graph because it's the lowest one. This would give us a minimum value at the vertex. The minimum value would not be 1. It would happen at 1, x equals 1, but it would actually be -2 because your vertex there was 1, -2. So the -2 would actually be your minimum value. Okay? Up here, your vertex is sitting up top of the mountain here, and so it has the largest y value of any point on this curve because they're all below. Remember, the higher you go up, the bigger the y value. The lower you go down, the smaller the y value. This is at 1, 2, 3, 4. So I have a maximum value, because it's the largest, of 4 when x is what? When x is -1. Because this point here is -1, 4. So in this case, I have a maximum value of +4. Okay? Now, if you have other types of polynomial functions that have more curves and such, as you'll see in section, I think it's section 2, then you can also have values that are maybe not the absolute largest or the absolute smallest, but are sometimes referred to as relative maximums and relative minimums. We're going to get to that in just a little bit. All right, so the maximum value or minimum value of a quadratic function is going to happen at the vertex. If a is greater than 0, like here, a was greater than 0, we have a minimum. If a is less than 0, like here, we have a maximum. A is greater than 0, a minimum. A is less than 0, a maximum. Now here it says find the maximum value or minimum value of each quadratic function. Well, to do that, since these are quadratics, I have to find the vertex. Now I notice right here, a is less than 0, so I'm going to have a max. And right here, a is greater than 0, so I'm going to have a minimum value. And I'm going to have them at the y value of the vertex. Oh, my mic's on? Oh, man. My mic's better be on. Otherwise, I'm doing a whole lot of talking for nothing. Okay, my mics are on. Very good. Whew. So what I'm going to do here is I'm going to find the x value of the vertex by using that opposite of b over 2a. And that's going to be, the opposite of -2 is +2 over 2 times -1. So that's 2 over -2. So that's -1. That's not my maximum value. That's where my maximum value occurs. So I have to find f of -1. Careful with all these negatives. Drive you crazy. So this is -1 squared, which is 1. And then the opposite of that is -1. Plus 2 is 1. Plus 3 is 4. There's my maximum value. +4. Here, x equals the opposite of b all over 2 times a. So this is going to be -8 over 4, which is -2. Again, that's not my minimum value. That's where it occurs at. That's the x value it occurs at. I have to find g of -2, which is 2 times -2 squared plus 8 times -2 minus 1. And see, that's going to be 4 times 2 is 8. Minus 16 is -8. Minus 1 is -9. Now, it doesn't always have to be a positive for a max or a negative for a min. You can have a maximum value that's negative. You can have a minimum value that's positive. It just kind of depends on the equation. So don't think that, hey, I got a maximum and it's negative. That can happen. In this case, it was positive. In this case, the minimum over here was a negative. Okay, now, one of the types of skills that you mentioned was that you have to be able... Oh, I did not bring the book here. Okay, so there's going to be a pause here for a second while I go grab the book. Be right back. I'm back. I got the book. So, I have, for quadratics, problems on page 143 that you're matching equations with the graphs. Whew, I ran out of shape. So now, what you would have to do here is to identify, first off, does my parabola open upward or downward? And what's my vertex? See, this one's already in vertex form. This is 2, 0, 2, 0, and it opens upward because A is positive. Well, that's this guy. There's your vertex at 2, 0, and it opens upward. So I know right away it's G. So that's what you're going to be doing to identify them. Look at number 6, vertex form. This is -1, -2, and it opens upward. -1, -2. Way up here, -1, -2. It's answer A. It opens upward. All right, now you say, what about one of these guys, like number 4? It's not in vertex form. Well, kind of it is. It's just that H is 0, because this is the same as the opposite of x squared plus 3. Can you see that? So this is also like, not that anybody in their right mind would write it this way, HK. See, what's being squared is x. X is like x minus 0. So it's 0, 3, and it opens downward. 0, 3, opens downward. That would be answer H. So you can try these problems this way for good practice. Page 143, 1 through 8. Do at least the odd ones so you can check to see if you're doing them right. But again, you look for two things. Find the vertex and determine if it opens upward or downward. I would be surprised if they have two problems in matching that have the same vertex that both open downward, but maybe one's skinnier than another one. If that's the case, then you'd have to look at the number that's being multiplied times the x squared, the A. See if it's skinnier or wider based on if A is big or if A is close to 0. All right, now, let's go on. All right, section 2.2. Okay, remember that polynomial functions are always continuous and smooth. Continuous means no breaks, no skips, jumps, holes. Smooth means no sharp corners, like the absolute value function. You may remember that the absolute value function kind of looks like this, kind of a V shape. Okay, that's continuous. There aren't any breaks or holes, but it's not smooth because it has a corner point, or what they call a cusp. And also, polynomial functions are not only continuous and smooth, but the domain is always the set of real numbers. Okay, now the key idea in this section is to try to sketch these things, and you're sketching them using the leading coefficient test and also using zeros and plotting some points. Now, the leading coefficients test is used to determine n behavior. N behavior. You know, does your graph on the right half end, does it go upward or downward? On the left end, does it go upward or downward? And you can tell that if it's a polynomial function, which is the long way to write it out this way, okay? And you look at the lead coefficient and the degree. N's the degree, A sub n is the lead coefficient. So here's the two situations if n is odd. Because if n is odd, one end goes up, one end goes down. Okay. What that means is if your lead coefficient is positive, it goes up and to the right and down and to the left. It rises to the right, it falls to the left. Okay? I made this part kind of dotted here just so you could see the n behavior kind of a thing. Okay? If n is, or A sub n, your lead coefficient is negative, then it kind of goes down and to the right, up and to the left. It rises to the left, it falls to the right, just the opposite of the other one. You're going to have to memorize these, okay? You're just going to have to flat out memorize them because you don't have to try to draw examples out every time you get to one of these. Now, it's a little bit different when the degree is even, like degree 2 or degree 4. I mean, think of your quadratics. That's degree 2. The ends either both go up or they both go down, depending on if it opens upward or downward. So it kind of works that way for all polynomial functions that have even degree as far as the end behavior. If you have even degree and the lead coefficient is positive, the ends go up. So it rises to the right and rises to the left. But if your lead coefficient is negative, then they fall to the right and they fall to the left. Okay, you have to keep that straight. He's going to have problems like that. In fact, let's just try some here. Describe the end behavior using for each using the leading coefficient test. Okay, descending order. There, my degree is 4, so that means it's even, and my lead coefficient is 1. So a sub n is positive. So since it's degree even and has a positive lead coefficient, you can see it right here, or maybe you can see it right here. This is going to rise to the right, rise to the left. Okay. Now here my lead coefficient is a -1, and my degree is odd. So degree odd, you don't have to write it out, you just have to keep it straight, and my lead coefficient is negative. Well, remember, if the degree is odd, one end goes up and one end goes down. Which one's which? Well, when the lead coefficient is negative, it goes down to the right, up and to the left. So it rises to the left, and it falls to the right. It rises to the left, it falls to the right. Okay? You can see that. There we go. All right, now this guy is not in descending order. The first thing I would do is maybe think of them in descending order by rewriting it. I can see my degree is even, and I have a negative lead coefficient, just the opposite of what happened above there in example A, because I had even degree, but I had a positive lead coefficient. So this one is going to fall to the right and fall to the left. So it falls to the right and it falls to the left. Okay? This guy here, he has an odd degree and a positive lead coefficient, so it's kind of the opposite of what happened in the example above there, because that was odd degree but a negative lead coefficient. So this one is going to rise to the right and it's going to fall to the left. Okay? Here we go. Now there's some more in section 2 as we're trying to get there. I hope I can get all this in before I have to be in the classroom here. I don't know. I may have to break this up into 2 videos here, this review. All right, when a polynomial function has degree n, then the following is true. These are kind of like notes. If it has degree n, okay, with respect to zeros, remember zeros are those numbers that when you plug them into the function for x, it makes the entire function equal to 0. It makes the y equal to 0. It's kind of like the x values of the x-intercepts. So when you have a polynomial function that's degree n, you can have at most n real zeros. N real zeros. You could get some imaginary zeros, which we haven't really talked about, and you haven't talked about in this book until I think in like the next section or 2, like section 4 or section 5. But we're only looking at real zeros here, and you can have no more than n. So if it's degree 6, you can have no more than 6. If it's degree 2, you can have no more than 2. And also, with curves that have higher degree, you can have different turning points, or maximums and minimums, relative maximums, relative minimums. I mentioned that earlier. But you can have no more than 1 less than the degree, n minus 1. So if it's degree 6, you can have no more than 5, 6 minus 1. If it's degree 10, you could have no more than 9. If it's degree 2, you could have no more than 1. Okay? Now what I'm going to do is I'm going to sketch f of x equals x to the 4th minus 4x squared. Okay, it's degree 4, positive lead coefficient. I know something about it already because of the leading coefficient test. I'm going to find my zeros, and I'm going to see if I can identify my relative extrema. I probably would need a calculator to do that. So in fact, just so I'm ready here, let me get my calculator all set. And what is this? This is x to the 4th minus 4x to the 2nd. I'll get this all ready here so that I can get to my graph here in a minute. So first things first, let's get some graph paper. Actually, first things first, let's find the zeros. Now, maybe even first things first, let's figure out the leading coefficient test here. The leading coefficient test, even degree, positive lead coefficient, it rises to the right and to the left. Okay. Now, zeros. And by the way, it's degree 4, so I can have as many as 4 real zeros. And it also means I can have as many as 3 relative extrema, relative max and mins, or turning points. So I'll keep that straight. But to find zeros, you set it, the function, equal to 0, and then hopefully it solves by factoring. And this one I can factor. I can factor out an x squared. That would give me x squared minus 4, which factors further. So I have x squared times x minus 2, x plus 2. Good old factoring coming into play here. And so, I mean, this is a x times x. So I have x squared equals 0 means x equals 0. I have x minus 2 equals 0. That means x equals 2. I have x plus 2 equals 0. I have x equals negative 2. Now, I could have as many as 4 real zeros, and it looks like I only have 3. But technically, since the factor x is repeated here, I technically have 4 because the 0 here has multiplicity 2. This has multiplicity 1. This has multiplicity 1. All right, so I have, these are not only my real zeros, my zeros are 0, 2, and negative 2. And of course, this has multiplicity 2, like I was saying before. But this also helps me because these are the x values of my x-intercepts. I have x-intercepts 0, 0, 2, 0, and negative 2, 0. So look what I'm going to do here. I'm going to get my, let's see, where's my graphing paper? I'm going to get my graphing paper over here. I'm going to make a set of axes here, hopefully big enough. Set my scale. And I'm going to graph these 3 points. I'm going to graph 0, 0, 2, 0, and negative 2, 0. That tells me I need more points. I mean, I know it goes up and to the right and up and to the left, but what's going on in here? Well, that's where your turning points are going to be happening here because you have a smooth curve. So you've got to come through here and you've got to get up to here, and then somehow you got to go back up before it's all said and done. So I would suggest that you make a T-chart with numbers on the ends where my zeros are and all my x-intercepts are, and also in between. So I'm going to plug in negative 3, negative 1, positive 1, and 3. Now I have to plug it back into my original function, which was f of x equals x to the 4th minus 4x squared. So if I plug negative 3 in, I get 81 minus 36. What is that, 45? Well, that's big. I'm not making my graph that big, I don't think. If I plug negative 1 in, I get 1 minus 4, that's negative 3. If I plug 1 in, I get negative 3. Looks like I'm going to have some symmetry here, maybe to my y-axis. And if I plug 3 in, I get 81, yeah, I get 45. So I'm going to have negative 1, negative 3. I'm going to have 1, negative 3. And it's way up here, way up here. So it's going to come down fast. It's going to hit here. Now, I don't know if this is my relative minimum right here at x equals 1 or not. Probably isn't. I'll have to use my calculator to find it. But I definitely think I'm going to hit right here at 0, 0, and that's going to be a relative maximum because there's a turning point. And it's real steep going up, real steep going up. Darn near vertical, but not vertical, but darn near vertical. That's how steep it is, okay? So I have 3 turning points, 1, 2, 3. I don't know if my turning points occur right at x equal 1 and negative 1. Let's see what my graph looks like here. So let me turn it on. Let me graph this. Oh, it's not going to be near easy enough to see. Well, not so bad. Let's zoom this in a little bit here. 2. Yeah, I messed up. It's lower than that. It looks like they could be occurring at x equals 1, but maybe, or x equals 1 and x equals negative 1. Let's see, what's that value there? let me change the y value just a little bit here. The minimum y value, let's go with -5 here, and let's see what the graph looks like. Yeah, it's kind of hard to tell, but it looks like it's a little bit to the left and a little bit to the right of -1 and 1, the actual minimum value. So I'd have to hit the trace and zip on down here. Let me arrow my way down there. All right, my y values are getting smaller, -3 points. Look right here for the y values. -3.677, -3.8, -3.97. Looks like it's going to be a y value of probably -4 there. So I'm going to have minimum values, relative minimum values of -4, and it looks like a little bit smaller than -1 and a little bit bigger than +1. So about 1.4. Well, I bet you it's the square root of 2, because it's pretty close to the square root of 2. Anyway, it would happen at x equal about 1.4, and because of the symmetry, x equals -1.4. So those would be your minimum values there. Okay, let me move this on over. Did I answer everything? I found the zeros, and I found the relative extrema. I had to use my calculator to do that. And this is what I was talking about before here as well. If f is a polynomial function, a is a real number, then the following statements are equivalent. That x equals a is a zero of the function. That x equals a is the solution to if I set the function equal to 0 and make an equation out of it, a polynomial equation. That x minus a would be a factor of that, because that's how I would get the root, the solution, and that a0 is an x-intercept. Now, they all sound like different things, but they're all related because they all involve the a here. So let's keep that straight. Find all zeros of the function. Set the function equal to 0. I can factor out an x squared. That leaves x squared minus x minus 20 is equal to 0. I can factor further. X minus 5 times x plus 4. Always check for the GCF. And I get x equals 0. Double root, multiplicity 2. I get x equal 5. And I get x equal -4 there. I just didn't put it all in there. So list the zeros. The zeros are 0, multiplicity 2, 5, and -4. Now here, this one looks, kind of messy. It is quadratic, so at least you could use the quadratic formula if you have to, but you set this thing equal to 0. I just don't think you probably want to with the fractions. And you solve this. Now, I would multiply through by 3 to get rid of the fractions. If I multiply both sides by 3, I get 5x squared plus 8x minus 4 equals 0. And with a little luck, this will factor. 2 and 2, 2 and 2. I need a plus 2 here, so I get plus 10, and a minus 2 here to get the minus 2x, and that'll give me the plus 8 in the middle. So 5x minus 2 equals 0, or x plus 2 equals 0. Add 2, divide by 5, I get a fraction, 2/5. Subtract 2, I get -2. No multiplicity is bigger than 1, so I have my zeros. Let's put it right up here, because I'm out of space, are 2/5 and -2. Okay. Now, I don't know if he's going to have this on there. I wanted to go ahead and put this on because I noticed that you'd had problems in an assignment. It says, find a polynomial function that has these zeros. Well, all you have to do when you have that is think of the fact that these are zeros, which means that x minus a is a factor of this polynomial. So I have x minus 2 and x minus a -6. So my function is x squared plus, I'm doing FOIL in my head, plus 4x minus 12. Over here, I would have f of x, that would be x minus 0, x minus 3, x minus 5. Well, x minus 0 is just x. So I would FOIL here, x squared minus 8x plus 15, and then I would distribute through by the x, and I would have f of x is equal to, x to the third minus 8x squared plus 15x. Now, I'm out of time because I've got to go set up for class and such, but I'm not all the way done with the review, although I did show you some good examples here. I'm going to have another video that's going to show you the rest of this review on section 2.3, and then I'm going to have try to put together a video for some practice problems for you as well. So make sure that you look through this, and if you have questions, be sure to ask me. Practice, practice, practice.